Good evening, Dr. Z. So this is the video for assignment number 7 for week 7. So in this one, I chose this option over here, option number 1, which was to create the credit risk classification application, you can say. So some of the things that we were supposed to do was use Lending Club or WRDS data. I went with the Lending Club data, which was from 2007 to 2018. And as I discussed with you, we didn't have any data after 2018, and you said that it was fine that we can use this data. And with that data, we were supposed to have some particular type of variables that we were supposed to work with. So credit scores, debt ratios, employment history. I chose a few others as well. We were supposed to do that, handle class imbalance, but basically seeing that the data is not skewed, that it is balanced, and then splitting the data. And there was model implementation, which means that using different kinds of machine learning algorithms to justify how are we going to be classifying the risk. So basically what I was working with was predicting default in the different kinds of loans that we had. It's for that, then making the model better, and consider class weights, and then comparing it with logistic regression, which is a simple one, and then the analysis, which goes forth. So let me first come to the report that I have generated. So as far as the introduction goes, basically just as I said that we are building a machine learning model to classify loan default risk using Lending Club data. Basically, I processed the data set and implemented a decision tree classifier, compared it with logistic regression, and analyzed the key factors which were part of the process. And as I was suggesting earlier, from Kaggle we have the 2007 to 2018 data, and basically we use that. So before I come into this one, so basically this shows the feature selection that I did. So from the data set that Kaggle provided, these are some of the variables that I basically chose, the columns that I chose. So FICO score, I chose that, debt to income ratio, employment history, loan status, verification status, and issue date. This was used for time-based splitting, and basically these two columns were right over there, FICO range low and FICO range high, and then I combined it into one FICO score as an average, and this was basically it. And with regards to the loan status, it was just in the columns it was given as defaulted, or basically still paying on it, or there were different kinds of categories. And I made that data, I processed that data into basically a particular set of numbers. So 0 for default, 1 for still paying, 2 for already paid, and and stuff like that, so that our analysis can get better. So let me go into VS Code and show you basically the code that I generated. Okay, and so this is the first part, and as I basically showed in the document that I was showing, these were the selected columns right over there. As I said, there was also loan amount. I forgot to add that into the report. We had the verification status. I also used the hardship status. I just wanted to see, like, if it was particularly helpful. But in my analysis later on, I found that it was not basically of much use. There was a lot of data that was not there, and basically imputing the data was just out of the question because of the missing field. So I just later on I just dropped that, but I just wanted to show that this is how I began. And this is how I filtered the data set, and I saved it to a file which is called Lending Club Filtered. I then proceeded on to cleaning up the data set first. I'm not going to show you the code like how I did that. What I basically did was that I used the median value, and I mean there were a few fields where there was no data, so I used the median to impute those values right over there, so that the data set can be complete, and so that there are no basically no NaN values, no empty values over there. And so with that, I saved that to another data set, which was the Lending Club cleaned data set right over here. So we didn't have any infinity values in this one, and no missing values in this one. So this was the clean data set, and then we proceeded further to building up our model. Yes, before moving further, I should tell you that this was the original file right over here. This was the data set that came by the Kaggle dataset. This is the one that I used, which I filtered first. So this was the file that I created, which was filtering for these selected columns right over there. And then as I said, the cleaned data set was right over here. So we move further to the class imbalance, basically going over that. And, these are some of the I imported Smote. So Smote was basically used to, handle the class imbalance. So the clean data set is the one that I'm going to be using. So first I checked, what was the class distribution, and I saw that, of course, the loans that had been paid were, much higher in number. They were, I think, about 70% in number or 80% in number, and the rest were much lower than that. And so I had to remove that class imbalance in order to have a successful machine learning program in order to go about. I should also tell you there were about 2 million data points in the data set. So yeah, we were working with a large number of data, and then of course, I implemented Smote right over here. Basically, I removed issue ID, which was supposed to be for the data, which we no longer needed. So this was right over here, and then basically I implemented the Smote learning and corrected the imbalance that was right over there, and I saved that to the lending club balanced CSV. So that was changed, and after that, so basically I used three kinds of the target, not the target variable, but the three classifications that we had in regards to the loan default. So these three balances were right over here. This is addressing the class imbalance, class balance that I was supposed to do that. So we divided the data into basically three, which was supposed to be fully paid and default, and fraction of a default, which means that late payments was another category that I wanted to introduce, even though ChatGPT was telling me that it was much easier to just classify the data into just two categories, which was just fully paid and default. But I just wanted to use late payments as another factor, which might be much helpful in predicting default. So basically I did I classified into values. So 0 was no default, 1 was moderate default risk, and 2 was high default risk. So as it is written right over here, after I implemented the Smote learning, which is synthetic minority oversampling technique to oversample minority class. So all the three classes were positioned to 33.3%, which was completely normal for three categories. So yeah, that was that. And as part of the assignment, we move on to the time-based data splitting. So let's go back to the VS Code. All right, so here's the file for the data split right over here. So we're using the lending club balanced after we had implemented the Smoke learning. So after that we were just first we ensure that the time is correctly sorted out, and after that we split the data. So what we are doing is that we are using 80% of the data set for training and 20% for testing. This is a very normal technique to go about. And what we did was that we implemented between 2007 to 2016 as part of the training data set, which is 80% of the data set, and then 20% was used for testing the data set. So testing, the model would use this for testing and just predicting if we are coming to the correct results. So 2017 and 2018 were used for testing, and 2007 to 2016 were used for training. And we save that splitting of the data set. We save them to Lending Club trained and Lending Club test right over here. And let me also show you the document right over here. Yes, so the reason why I did that was basically this ensures that future loan data is predicted based on past trends rather than just a random split. So I just did not want to do a random split, but basically splitting the data, between the years to just like use past trends as the model going forward. Anyway, we move on to the model implementation. So I use the decision tree classifier. Before I actually go into this, I should show you the code first. So the decision tree classifier is right over here. So we have these two data sets, and basically we are using accuracy score, precision score, recall score, F1 score, basically as our model analysis. Basically, how well does the model work? And I've loaded the data set right over here, and we have every single column used over here except for issue D, which is for the time, and loan default. This is not supposed to be used here. It is used to be used as the var variable because we are predicting the loan default using the other categories that we had. And so, training our decision tree classifier, these were some of the, basically the parameters that I use, maximum depth, minimum sample split, minimum sample leaf, class weight balanced, random state. So this was, how we did that. And basically, evaluating the model performance and seeing, what basically our scores for this model came out to be. So let me show you first, the screenshot that I took, of what this decision tree showed. Yes, so after having run that file, what we this was the model that was coming out to be. The accuracy was just about 48%, which was not really good. We had precision at 48%, again 48.49, recall was 48.25, F1 score was 48.33. So this was basically the results that we had coming out to be, and this is for the different classes that we had, for no low default, mid default, high default. So these were the scores that came out to be that the model is this much successful in predicting these results. So this was not as great, and therefore we had the part of the assignment was to better basically the model that we had. So let's go back to our code basically. And so, okay, yeah, here's the file. So decision tree tuning, which was going to be right over here. So in order to better the results, so we're using the same columns and everything for predicting the result, but the parameters are now changed. So notice that all these these parameters right over there, we only had included just one single value for the parameters. So the max that I think was 10, so we used 5, 10, 15, 20 over here. Minimum sample split 10, 50, 100. Minimum sample sleeve 10, 20, 50. So different parameter values I used over here, so that in this one we're both using both Gini and entropy as the criterion right over here. So in order to get better result, we also used grid search CV right over here, which is the cross validation. So we did I think it was a 5-factor cross validation. Let me actually confirm over here. Um, yes, I think it was. Yeah. So here we are. So 5-fold cross validation is what we used. So the best parameters, what we came out to be was this right over here. So let's go back to the code. Yeah, so after that was done, basically just seeing what the score came out to be, and how is this model becoming any better with this tuning that we are doing. I also want to tell you that for visualization purposes, the decision tree model just in order to visualize that, it was saved to a PKL file, which I have right over here. It's actually too long, so I cannot actually show you exactly just how it's coming out to be. Just bear in mind that how I saw it, it was coming out to be as a decision tree is supposed to be. So I'm not going to be showing that, but let me show you what the results came out to be after hyper tuning this model right over here. So let me show the screenshot. The reason why I'm showing the screenshot is because it takes a long time when I run this file in order to show it. So it's better actually that I just show the screenshot. So look at that right over here. Instantly, you can see that yes, the model is much better now. Before, with regards to the previous model, so accuracy is now at 60.67%, precision is almost 60%, recall 60%, F1 score is the same way, and at every single class, you can see that the model has become better. Now, of course, we would imagine that in order to make the model better, we should be going higher in our precision, in our accuracy. We should be it would be much better if we were close to 90% or something, but we are doing this for basically for our academic purposes, and the purpose of this assignment is just to show that we know how to proceed further now. Of course, I imagine that we have other machine learning models that can help us better the model. So I tried to use random forest, as part of this assignment, but it took hours, to implement, and basically it was just not good enough that I should make it part of the assignment. Of course, I could go to XG, like gradient boost, or other machine learning models as well. So I did not include that as part of the assignment, but I just kept it to this, so that I can showcase that I actually know, basically, as the purposes of this assignment, that I know what I'm doing. If it was part of a project, of course, I would have gone much further to make the model better. But for our purposes, let's assume that this is the best model that we had. Let's go back to the code. So the next part was to just compare to a regular logistic regression right over here. So of course the same variables were used. The predicted variable again is lone default. The predicting variables are of course the FICO scores and DTI and employment status and employment history and all of that. So these are the parameters right over here, and then of course we finally have the results that came out to be. So just printing the results right over here. So let me also show you the screenshot. All right, so with this logistic regression, we can see that the model, that we have created over here with the logistic regression is even worse than the first decision tree. So logistic regression is not the way moving forward. We can see that accuracy is 42%, precision 42%. Basically, everything is like 42, 42 and a half, close to that. And we can see like on every class that we have, of course, we have much lower, much weaker results than we had with the best decision tree that we created after hypertuning. So of course we're going to go with the hypertuned decision tree model, with the five-fold cross validation model that we have created. Okay, so we're finally moving to the analysis part. Once we have made the model, just like seeing that this is our best model moving forward. So what results come out to be? Of course, we have shown that the model is this much, better in predicting the result, but, to move to the rest of the analysis. So part of the analysis over here was just evaluating using precision recall and F1 score, which we have already done. Then we have to analyze the feature importance, visualize decision tree structure. I've already mentioned this, and consider the economic implications of misclassification. So what happens over here? So let's go back to the code, or before that, actually, let me go on to our report right over here. So this just shows the logistic regression performance as I was showing over here. So the feature importance is right over here. We can see the FICO score was the most significant factor in predicting the default risk. But actually, before that, let me go back to the. So let's move on to the analysis one. So we have this right over here. We have the training data set and the test data set, just to see what we came out to be. Loading the decision tree model, what it predicted, the classifications, converting it to data frames, and then saving it to classification reports. And then basically this is the feature importance, just to see which features were the most important, and then saving that to a feature importance CSV. I'm not going to show the CSV file. There's no use showing that, but I am going to show you the visualization that I saved. So just give me one moment. And so we have this feature importance right over here. So we can see verification status, FICO score, debt to income ratio, the loan amount, and employment length. So we can see that the most important feature that we see, I created this important score right over here. The most important one we can see, which is more significant than anything else, as we can see over here, was the employment length. So how long you were employed for was the most important factor, in predicting whether you're going to default or not. So of course we had different kinds of values. We had from 0 years to all the way to 10 years, and then 10 plus years. I also should mention that anything that was written as 10 plus in the original data set, I converted that to 10, which is going to be the maximum one, because we don't know if it is going on to 15 years, 20 years, 25 years, 30 years. We do not know that. So it was written as 10 plus. So I already concluded that 10 is going to be the maximum value that we have. So this was the most significant factor. We can see the loan amount was the second one, then DTI followed by the FICO score, and I've also changed that as part of my report right over here. So employment length was the most significant factor in predicting default risk. FICO was less important, but it still contributed. So one would imagine that FICO score would be very important, but it wasn't the most important. Of course, it was still important, and debt to income ratio was also one of the um, important ones. So let's go back to the code over here. So this was the feature classification as promised. This is the plot code right over here. And then we move on to the economic implications. So, economic implications. So, what I did was that in the economic implications, I identified that the thing that we're going to be discussing is false positives and false negatives. So, in predicting the default, how many false positives we have, how many false negatives we have, and this is going to be the economic implication that comes out, after predicting these defaults. So after implementing this machine learning program. So we have that right over here. And also, I just did the same thing right over here, but I also, did that in a tabular form just to show, what the percentages basically came out to be. And so let's go back to the report as the final thing of this assignment. So these are the economic implications as I listed right over here. So we have two misclassifications type, which is going to be false positives and false negatives. So this is a bit skewed right over here. So basically, the count of false positives was 50,069 values that we can consider false positives, and false negatives were 60 to 62,446. So percentage of the total ones that are, of the default ones that we had, 7.75% were false positives and 9.67% were false negatives. Now, of course, individually, these are not huge values. And, this is like one of the better things of this model. Of course, the model could be made better, just like I said, using random forest or a gradient boost or, other machine learning programs such as this in order to better those results. But even this one is, for our academic purposes, fine. So for false positives, for 7.75%, the impact would be the customers denied loans unnecessarily, which would lead to lost revenue. So this would be the impact of the false positives. And for the false negatives that we have, it would be the impact would be high risk borrowers, are approved, and we have potential for financial losses. So that is right over here. You know, False positives may result in lost lending opportunities for low risk borrowers, and for false negatives, lenders face increased risk of defaults, leading to financial losses. Given these results, banks should carefully balance their credit risk models to minimize both false positives and false negative rates. So we have over here, and this just includes the conclusion and recommendations, basically. So, just like as I was saying, for future considerations, we can use ensemble models for just like gradient boosting, which would improve predictive performances, and we should penalize false negatives in order to make the data better, and more recent data if it was available. Of course, we can use that to enhance our prediction. So that is right over here. Thank you so much. This was my assignment. I hope you like it.